Now we're going to look at an axial bar where the material is going to change partway through. So this is going to fall outside of what we can solve analytically from the previous section where we needed constant material, which is to say we needed a constant Young's modulus and density in order to use the PDE and the solution that comes from. And in this one we have a constant cross-section though, so at least the A is going to be constant all the way through. So what we're going to look at here is what happens when the bar is half steel and half brass. And in scenario A, like the picture shows, the steel is attached to the wall and the brass is a free end. And in scenario B, what if the brass is attached to the wall and the steel is the free end? So the bar is the same in both scenarios. It's just the boundary condition, which side is attached to the wall, that's going to change. And what we're looking for here are the first two natural frequencies of the system using the FEA. So like in the previous example, we don't know analytically what the solution should be because we cannot solve this one analytically, but we will be able to look for convergence in our FEA solution and maybe have some idea of how valid this solution is by finding an analytic solution to a problem that we do know how to solve. Going into the code, we're going to start with the scenario A when the steel is attached to the wall. So the code is going to look similar to what we saw in the previous example with the tapered beam, where there were properties that were changing as we went from element to element. In that example, the cross-sectional area was changing. In this one, the material is changing halfway through the beam. So I'm going to here, I want to demonstrate convergence, so I don't know how many nodes it's going to take or how many elements it's going to take to converge, so I'm going to start with 3 nodes up to 200. And notice what I'm doing here is a little bit different than the previous one. I'm going to increment my nodes by 2. And why I'm doing this is I always want a node exactly at the center of the beam because that is where my material is going to switch from steel to brass, or in part B, from brass to steel as I go left to right. So the benefit of always having an odd number of nodes means I'm always going to have an even number of elements. And the benefit of that is I'm not going to be switching kind of midway through that I have an element that's half steel, half brass. So the rule is for my elements that every element itself has to have a constant Young's modulus, density, and area. I can't guarantee that if I have an even number of nodes, and we'll see what happens if we let it have an even number of nodes, that it's not going to be necessarily wrong, and as we add more and more nodes, it's not going to really make a difference because the error we're introducing is going to be relatively small. But for this one, I'll keep it odd so we can see the convergence and then see what happens if we don't. All right, so putting in my parameters here, again tracking just the first 2 natural frequencies, putting in the given parameters, again my Young's modulus of the steel and the brass are going to be different as I transition halfway through, and then the density, the volumetric density of the steel and the brass are different too. So same basic structure. I'm going to keep making K and M matrices that are bigger and bigger and bigger as I add more nodes into my calculation here, dynamically making the map list as I increase the number of nodes, and the length of each element is going to get smaller as I add more nodes and more elements. Then I go in and I'm going to make my elemental stiffness and mass matrices and then make my global matrices from there. So here's what's different is I have to know where in the structure I am, so I know is the element that I'm creating made of steel or is it made of brass. So I have this check in here because in this example there's only 2 possibilities. It's either a steel element or a brass element. So what I'm going to check here is if I'm on the jth element, I want to know is the j I'm on in the first half or the second half of my beam. So for example here, if I'm in the first half, that means that j over the number of elements I have is less than 0.5. And I can only have an even number of elements the way I'm doing it right now because I can only have an odd number of nodes. And we'll change that and see what happens. But so that means if I'm less than or equal to 0.5, I'm in the left half, it's made of steel. So I assign for that element steel's Young's modulus and steel's density. Otherwise, if I'm in the second half, the right half, it's made of brass. So I'm going to assign the Young's modulus for the brass and the density for the brass. So it's going to check each element I'm on, am I left half or right half? Am I steel? Am I brass? Then the rest of this really looks the same. It's going to calculate the stiffness in the mass matrix based on the correct Young's modulus and the correct density for the material that I am made of. And then I'm going to apply my boundary conditions. I am here, have a wall on my left or a fixed end on my left, a free end on the right, so I only need to eliminate the first row and first column in order to enforce that one displacement boundary condition, u of 1 is equal to 0. That free end, nothing needs to be enforced there. I don't need to put in anywhere here that I have 0 strain there, just on the displacement. And then I'm going to calculate the natural frequencies for that number of nodes and just save the lowest 2 after I sort it, so the first and the second. So that's the basic premise of what the code is doing here. Again, meshing it out, checking if for each element, am I in the left half or the right half, so I know what the local mass and stiffness matrix should use for its E and its rho, and then put it into the global. All right, so I'm going to do this first for the steel being attached to the wall. Okay, so I run that, and let's look at the convergence. Again, I don't know up front what the answer should be, but I can look at, does it at least converge? If I don't have convergence, I know I cannot trust my answer. But here, for the first natural frequency, we see that by 200 elements, it looks to have converged to one value. So let's just look at the last one here. So the lowest natural frequency, about 7,070, 7,068 radians per second. And the second natural frequency, 19,000 radians per second. And again, this is when the steel is attached to the wall and the brass is the free end. They've converged, so that's a good sign, but I don't necessarily know if these values are any good. The 7,070 versus the 19,000 for the first two. So I cannot solve this one analytically, but I can again get some rough estimates of what these values probably should be near if I analytically solve a simpler problem, a simpler version of the problem that I will be able to get the exact solution for. So I'll come back to that. I'll put these two values aside though in the meantime. And I'll move on to scenario B so we can at least have some numbers here where brass is attached to the wall and steel is the free end. And the setup to this one, it has its own code. Really everything about it is the same. The only difference is here in when I'm assigning per element what material is it made out of. Now, if it's in the first half, the left half, it's brass. So Young's modulus and density are those of brass. And if I'm in the right half, then Young's modulus, density are those of steel. Everything else, though, about this problem is the same. So quickly, I can run this, and I can get what the natural frequencies are when I switch which side is connected to the wall. And if I look at its convergence, I have converged, so that's a good sign. And if I look at the values, I get that the first natural frequency, 5,876 radians per second, and my second natural frequency, 19,820 radians per second. Again, both of them have converged by 200 elements. It's converged, that's a good sign. It's different than the first time I ran this, where the steel was connected to the wall rather than the brass. Both of my natural frequencies have changed, which should make sense because natural frequencies in continuous systems are going to be dependent on the boundary conditions. And even though it's the exact same beam, the fact that a different side of it is connected to the wall should have an influence probably over what the natural frequencies are. So that's not really unusual here, but they are different answers than I got for scenario A. But again, they've converged, but have they converged to necessarily the right number? I don't know yet, and I don't necessarily have a great way to validate that. But like I was saying before, I can at least ground this in maybe a similar problem that I do know what the answer should be. And to do that, if I simplified this problem and have it instead made of two materials, I had it made of only one material, that's a problem I can solve analytically. It's certainly a different problem, but at least it's one I can get an answer to that I know is right because it comes from the theory, it comes from the analytic solution. I already have a constant cross-section, so that's not an issue. But what I can look at is, what if I have this fixed free beam and it's entirely made of steel? Or what if I have this fixed free beam and it were entirely made of brass? Both of those I can solve. I know how to find the natural frequency in a fixed free beam or bar that has one material and a constant cross-section. So I can calculate what those natural frequencies should be and at least compare it to what I'm getting in the FEA. They're not, and I should not expect them to be the same as what I'm getting, but at least it's going to ground my answer in a little bit of validation. If I run those calculations, assuming the beam were all steel and all brass, these are the first two natural frequencies I get. Again, I know how to calculate that from the theory using this Young's modulus and this rho. So really what's changing between these is that C value in my calculations. So if this were all made of steel, my first natural frequency would be 7,930 radians per second. And if it were made of all brass, it would be 5,470. And what I get from the FEA, this is when the steel is attached to the wall, I got from the FEA 7,068 at the time when it converged. So that happened around 45 nodes. And we see here that the FEA is, the natural frequency is between an all steel and an all brass bar, which, I mean, that's reassuring because it's half steel, half brass. It's not halfway in between the natural frequencies, but we really can't expect that to be the case in these types of complicated systems, but it is between them. And probably more importantly, the magnitude, 4 digits of magnitude, is the same as all steel or all brass. So our answer converged, and it converged to what seems to be a reasonable number based on a simplified version of this if it were all steel or all brass. It happens to be in between. We can't expect that to necessarily happen, but that does give us some additional confidence, I think, in the answer that we came up with. And for the second natural frequency, if it were all steel, we get about 24,000 radians per second versus 16,400 for all brass. And again, from the FEA, once it converged, we're getting a number in between those two values. So for steel mounted to the wall, these values seem reasonable based on the analytics, and they have converged. So I would say we can be pretty confident in these first two natural frequencies being correct for this setup using the FEA. Now we can look at the results when scenario B, the brass was attached to the wall. Again, these are the results from the FEA from when it converged. And notice between the brass and the steel, we did get certainly a different first natural frequency, and the second natural frequency is different as well when those boundary conditions changed. All steel, all brass, that is the same as it was. And let's look at the results here. From the FEA, when the brass was attached to the wall, again, we were in between an all steel and an all brass bar. And this time, actually, we're closer from the FEA, we're closer to the value of an all brass. We can't necessarily predict that just because the brass is attached to the wall. I don't think we knew beforehand that necessarily the natural frequency should be more like the brass than the steel. But it's in between. So again, it converged, and it's in between our two estimates of the simplified versions of the problem. And if we look at the 19,840 from using the FEA, again, that falls in between the all steel and the all brass. But actually the opposite trend is true here, that it's actually higher than it was when the steel was attached to the wall. So we cannot necessarily say beforehand we think it should be closer to the brass, because this actually did the opposite. But to ground our solutions, again, both cases, we saw convergence by around 45 nodes. We went up to 200. We definitely saw convergence for these first two natural frequencies, and we are trying to validate them with some analytic approach, even though the analytic approach is a different problem because it's not half steel, half brass. We can only do it with all steel or all brass. But with all of this evidence coming together, these answers we're getting from the FEA seem to be pretty good estimates as to what the natural frequencies of this compound beam should be.